Welcome to this video. My name is Mark Scythian. The date today is January 20th, 2025. So in this video, we're going to focus on designing an AC RLC series electrical circuit to energize an AC motor to 10 amps at 25 volts AC with a frequency of 50 hertz. So the first thing we want to do is figure out what frequency is also equal to, and it is this equation here. So if we solve for equal values of L inductance and C capacitance, then we can then assign equal inductance and capacitance values. So we can just solve for the equality to LC. And so we do so here by applying the rules of algebraic exponents, and we can cancel out the square root and then make a nice symmetrical value for LC by getting the base square root. So we have equal inductance in henries and farads and capacitance. So we do that first and then scale it down to the micro henries and microfarads values. So now we know also that the power factor will be 1.0, again establishing a resonant circuit. So from this we can calculate the inductive reactance and then the capacitive reactance. So upon doing so, we may not get equal 1 ohm values. So we actually do not, but what matters is that the inductance and the capacitance are equal. So the power factor is actually unity power factor of 1.0. So this simplifies the design and accuracy. So now all we have left is to solve for the resistance, which is the product of the impedance times the cosine of the phase angle. So if we get the inverse cosine of the power factor, we get the phase angle across the voltage and current sine waves. So inverse cosine of a power factor of 1 is 0 degrees phase angle. So we can just assign cosine of 0 degrees or 1 times 1 ohm. So the goal is just to use 1 ohm of impedance Z to equal 1 ohm of resistance, but this may not be correct, but at least we have an equality, and then we can do some adjustment corrections thereafter. So we'll just assign 1 ohm to the resistor. So now we have AC RLC series impedance, and we can use this equation for the series RLC impedance, unlike the parallel Z sub P. And so we just plug in the values and we calculate counterintuitively actually not an equal impedance to the resistance. We actually get 9.95 ohms. So then we must assume that the resistance is now 9.95 ohms. So we'll just enter that in, but we still have to test it to see if our current value is what we want. So we can divide the RMS total voltage into the impedance that was calculated, and we actually do not get what we need. We get 2.51 when we need 10 amps. So what we can do is just make 10 amps equal to the RMS voltage divided into some impedance, Z sub S, and then solve for what we need. We actually need 2.5 ohms of impedance. But because we kept the equalities consistent between the R and the Z, it is accurate. So now we know for sure that the resistance is actually 2.5 ohms, consistent with the 2.5 ohms of impedance. So now all we do is divide the RMS voltage into the impedance. We get 10 amps, so that's good there. And then we have the true or real power flowing to the motor, our AC motor, so that's the RMS voltage times the RMS current times the power factor. And we do get 0.25 kilowatts of AC electrical true power. So we'll write that in there. And then we have AC true power and our power factor and our impedance value placed next to the motor. And now we are complete. So try the one-to-one method, and then from there after you can then adjust it for what you need, because the circuit is in resonance. So when you calculate the correct impedance, it is also equal to the resistance. Thank you for watching this video and have a great day.